Today we are going to talk about the material in section 10.2 and in section 10.4, and then we will also be looking at some practice problems. In 10.2, we're going to talk about triangles. So last week we learned about points and angles and lines and planes, and now we're going to build on those ideas. And in math, we like to start with definitions so that we can be really clear what we're talking about. And we have the definition of a triangle here. It's a closed geometric figure that has three sides, all of which lie on a flat surface or plane. So if I imagine this slide here as a plane, a flat surface, which of course it is, I can draw that figure that we're talking about. So it has three sides and it's closed. So this fits the definition of a triangle. This doesn't fit the definition because it has four sides, but it's closed, but it has four sides, so this doesn't fit our definition. And then this has three sides, but it's not closed. So that doesn't fit our definition either. So one thing that's really useful in math when you learn a new definition is to kind of look and see what fits the definition and what doesn't. The next thing that we're going to talk about is an important theorem called Euclid's theorem, but let's first talk what a theorem is. And a theorem is something that we can prove. So we take information that we already know to be true, definitions, other theorems, whatever we've added to our body of knowledge. And if we can come up with something new based on putting all of the things that we already know to be true together, then we can write a theorem and we can prove something new to be true. So for Euclid's theorem, we're going to first think about if I have a parallel line and then a point. So imagine this bottom line and this point. Euclid made an assumption that there's only one way to draw a parallel line through this point and parallel to this line. And if you kind of think about it and try drawing it, you'll notice that there really is only one way to do that. And so if we take this assumption and then we add to it what we learned last week with our parallel lines and then the transversal that was cutting through them. So thinking about the two blue lines, well, this line through A and C, and then this line going through point B, those two lines are parallel. So we might put our little parallel symbol on them. And then if I think about this line through AB, so if I think about extending this and making it a line, now it's a transversal through there. And remember, when we have a transversal, we know that these opposite lines, or these angles that are opposite that transversal and interior to the parallel lines, are congruent. So that means angles 1 and 2 have the same measure. The measure of angle 1 is equal to the measure of angle 2. What else do we know? Well, we can also extend the line on the right side. So I can extend this line through BC, and now I have a transversal. And now notice that angles 3 and 4 are alternate interior angles. So we know that they also have equal measures. And then what do I know about angles 2, 5, and 4? Well, they make a straight angle, don't they? This angle here is 180 degrees. And we know that because it makes a straight line. So the measure of angle 2 plus the measure of angle 5 plus the measure of angle 4 has to be equal to 180 degrees because that's a straight angle. But down here we said, oh wait, angle 1 and angle 2 are the same. So I can replace this with angle 1. And then angle 4 and angle 3 here we showed were the same. So I can replace this measure of angle 4 with measure of angle 3. So that means the angles of 1, 5, and 3 also have to add up to 180 degrees. And we can create any triangle this way by taking one side of the triangle and then drawing a parallel line through the other point. So this is how Euclid proved that the sum of the measures of the three angles of any triangle is 180 degrees. And we have various ways of doing this. If you took a geometry class in high school, you might have had to do two column proofs where on one side you wrote a statement and then on the other side you wrote how you knew that that statement was true. And we just sort of outlined the proof here. The important thing to remember is that anytime you have a triangle, the three angles have to be equal to 180 degrees. So as long as I know two of those angle measures, I can always figure out the third one. And here's an example of that. I have this triangle ABC, and I know that angle B is 120 degrees, and angle C has a measure of 17 degrees, and I want to know what the measure of angle A is. So if I wanted to write out the algebra for solving this, I would start by writing what we know, that the three angles in a triangle, angle A plus angle B plus the measure of angle C, has to be equal to 180 degrees. And then I can replace the ones that I know. I know angle B has measure 120, so I can replace measure of angle B here with 120 degrees. And I know that angle C is 17 degrees, so I can replace measure of angle C with 17 degrees. And now I can rewrite line 1, replacing those to say measure of angle A plus 120 degrees plus 17 degrees is equal to 180 degrees. In my next step, then, I can simplify this side. So I'm going to add 120 to 17 and rewrite that. And so I get measure of angle A plus 137 degrees equals 180 degrees. And now what I can do is I can just subtract 137 from the left side, subtract 137 from the right side, which gives me 180 minus 137. And now I have the measure of angle A, 43 degrees. So now we have another way. Last week we talked about vertical angles having the same measure. And then we talked about the situation where we had two parallel lines with a transversal, and we looked at all of the angles that were congruent there. And now we're going to build on that with this idea that a triangle adds up to 180, and we can solve a lot of new situations like this one. And whenever I have a problem like this one, I like to kind of combine it with writing in some of the things that I know based on other things that I know, as well as writing in some of the arithmetic that I'm going to do. So one of the first things that I'm going to do is look for any angles that I can write. And right away, remember this little square means that this is a 90-degree angle. And then since these two angles here have to add up to 180, right? This is a straight line. That means angle 1 is also 90 degrees. And now I can use the fact that the three angles in a triangle have to add up to 180 to figure out angle 2. And that's what we've done here. Measure of angle 1 plus measure of angle 2 plus 43 degrees, this angle, has to be 180. And then we know angle 1 is 90 degrees. So we can simplify this and we get that the measure of angle 2 plus 133, which is the sum of 90 and 43, equals 180. And then subtracting 133 degrees from both sides, we find out the measure of angle 2 is 47 degrees. And now once I know that that's 47 degrees, I notice over here a vertical angle. So I know that angle 3 is also 47 degrees. And now that I know this angle, I can find angle 4 because I know that the 47-degree angle plus the 60-degree angle plus whatever measure angle 4 has to equal to 180 degrees because these three angles form a triangle. And then I can simplify. So 40 and 67 gives me 107 degrees. And then just copying everything else down. And then subtracting 117 degrees from both sides. And now I know the measure of angle 4 is 63 degrees. And so now I might write that in there. That's 63 degrees. And then the last thing I can do to find the measure of angle 5 is I know that these two angles, 4 and 5, also have to be equal to 180. So I know that the measure of angle 5 is going to be 180 degrees minus whatever angle 4 was, which was 63 degrees. So that is 117 degrees. Huh. It was the same thing that we got when we added these two up, wasn't it? And I said 117. I did that wrong. Let's correct that. So if you were confused about what I did here, yeah, that's because I did it wrong. So let's fix that. That means this is wrong too. So 47 plus 60 should be 107. I noticed that when I redrew it. All right, 107 degrees. So that means I would have had to subtract 107 degrees from both sides. And I would get 73 degrees for angle 4. And by the way, if you ever notice a mistake, please be sure to let me know, because it's easy to make those little arithmetic mistakes when I start working too quickly. All right, and then so here we had 180 minus 73, which gives us exactly what those two angles added up to, 107 degrees. And we actually have a theorem that tells us that. So this angle here has the same measure as the sum of these two angles. Anytime we have a triangle, we call this an exterior angle. And it has the same measure as the sum of the two other angles in the triangle. So that's one way we could use Euclid's theorem, kind of combining it with what we know about vertical angles and what we know about supplementary angles. We also define different types of triangles. So last week we talked about a right angle and an acute angle and an obtuse angle. We also classify triangles based on the angles that they have. When a triangle has all acute angles, that means all angles that are less than 90 degrees, like this one. You can see they're all less than 90 degrees. So this is called an acute triangle. When a triangle has one angle that measures 90 degrees, like this one, remember this symbol means 90 degrees, we call it a right triangle. Could a triangle have more than one 90-degree angle? Well, remember the angles in a triangle have to add up to 180. So if one of them is 90, that means we only have 180 minus 90 degrees left, right? So the other two can only measure 180 minus 90, which is 90. So we couldn't have another 90-degree because then we wouldn't be able to make the third angle. So a right triangle has exactly one angle measuring 90 degrees, whereas an acute triangle has all three angles are less than 90. An obtuse triangle also has just one angle that's obtuse for the same reason that the right triangle, right? Because the obtuse angle is going to be more than 90. That means we don't even have 90 degrees left for these other two. So they have to be acute. We can also classify by sides. So when we have two sides that have the same length, like in this triangle, this little symbol here and this symbol here means those sides have the same measure. We call this an isosceles triangle. And we have a theorem that we can use. We can prove that if these two sides are equal, then the angles opposite them. So this angle is opposite this side, and this angle is opposite this side. So these two opposite angles are also congruent. They have the same measure. So an isosceles triangle has both two sides and two angles with the same measure. And then we have an equilateral triangle, also called an equiangular, because all of the sides and all of the angles are exactly the same. And since we have 180 degrees in the triangle, each angle is going to be 180 divided by 3. which is 60 degrees. So each angle is 60, and then the sides are the same. The sides can be anything we want. They could be really tiny like that, or they could be much bigger like that. And then we have a scalene triangle. And that's just a triangle where no two sides have the same length. All of the sides have different lengths. And so if you're answering questions about those types of triangles in the homework, just always go back to that definition and make sure that you're following the definition when you're deciding if a triangle fits one of those categories. Another thing that we talk about is, first, we talk about triangles that are exactly the same, and we say that they're congruent. And those are important in proofs. But when we're solving real world problems, what's even more important are what we call similar figures. And triangles are a type of figure. So similar triangles are just similar figures that happen to be triangles. And how we know that they're similar is that they have the same shape, but they might have different sizes. So we just saw that on the last page with the equilateral triangle. We could have a little tiny equilateral triangle, or we could have a much bigger equilateral triangle. But as long as all three angles are 60 degrees, they're both equilateral, so these would be similar triangles. Okay. So how do I recognize similar triangles? Well, the angles have to all be equal. All three angles are equal. Can't just have two angles, can't just have one angle. I have to have all three angles equal. But the sides, as we see in this example up above with the equilateral triangles, the sides don't have to be the same. But it turns out what we know when we do have these similar figures is that if the angles are all the same, then the sides all have the same ratio. And that can help us to solve a lot of problems. We also define the angles that have the same measure. We call those corresponding angles. And then opposite those corresponding angles are corresponding sides. So let's draw a picture of what we mean by that. And we'll do this triangle and then this triangle. And let's agree that these angles, so this means these angles have the same measure. And then I'm going to draw 2 here to show that these angles have the same measure. And then 3 little lines here show that these angles have the same measure. So these angles are corresponding. This angle A corresponds to angle D, and angle B corresponds to angle E, and angle C corresponds to angle F. And then I might also draw in the side. So the side that's opposite angle D, I'm going to call side little d. And the side opposite angle E, I'm going to call side little e. And the side opposite angle F, I'm going to call side little f. And then I can do the same thing. Here, opposite angle A is side little a. And opposite angle B is side little b. And opposite angle C is side little c. So we have angle B and E are corresponding angles, and then the side B and side E are corresponding sides. And so then we know that they have similar ratios. So for example, if side A has a measure of 2, and side D has a measure of 4, what that means is all of the corresponding sides in this bigger triangle, DEF, are going to be twice as big as the corresponding side in the smaller triangle. So if I know that side B has a length of 1, E has to be twice as big because D is twice as big as A, so E would have to be 2. And so we can use this information to solve a lot of problems, to find distances. I used it in my front yard to figure out how tall a tree was that my husband and his friends wanted to cut down to make sure that it wouldn't hit any of the cars on the street, just by using a triangle made from the shadow of the tree and the shadow of my husband. And we were able to figure that out. So who says geometry is not useful in everyday life, not me. And here's another example of those similar triangles. Okay. So ABC and DEF are similar. This is another way of doing that notation. So in the previous slide, I did 3 little arcs, but we can also just draw 1 arc and then put 2 lines in it. So we've got the 2 lines here and the 2 lines here. That means angles C and F are similar or are corresponding. And then that means that this side AB and this side DE are the corresponding sides. And you notice that the side, they're drawn in the same orientation. So you can see that all of the sides in the larger triangle ABC are twice as big as those in DEF. And we can use this information to find missing links. In this problem, I have these 2 triangles and I need to find the length of side that has the X. And so what I have to do is I have to first see, are these actually similar triangles? Well, we've got this angle is congruent to this angle. But I need to know that all 3 are congruent. And fortunately, these 2 are vertical angles. So I know that those have to be congruent. And then what else do I know? Well, I know the angles have to add up to 180 degrees. So if these 2 are the same, the third one would have to be the same in order for both triangles to have 180 degrees. And so now what I can do is I can compare, and so let's call this the angle with 1 mark. So notice that the side opposite the angle with 1 mark is 5 in this triangle, and it's 8 in this triangle. So these are corresponding angles. Actually, they're corresponding sides, aren't they? And this one is in, we'll call this triangle A, B, C, and this one will be C, D, E. So side 5 is part of triangle ABC, and the side that's 8 inches is part of triangle CDE. And so when I do this comparison, I need to make sure that I'm comparing sides from the same from the same triangle. Both need to be in my numerator. So these are 2 corresponding sides, 5 and 8. And then I look over here, and opposite this angle in this triangle is a 7-inch, and in this triangle, it's the one I'm looking for. So now I can write 7 over x. And these sides have to have the same ratio. So I know that whatever the ratio is of those corresponding sides in the smaller triangle to the larger triangle has to be equal to any other corresponding sides. And if I knew one of these other ones, either CD or AC, then I could find that as well. And then now all I have to do is find this. And how do I solve this? We can use what we call cross multiply. So anytime we have an equal sign with a fraction on both sides, we know that numerator times denominator this way has to be equal to numerator times denominator this way. So I have 5x is 56 and x is 56 over 5, which we can also write as, let's see, 11 1/5 or 11.2. Could also do that on your calculator. And then we might want to check and see, does that make sense? So I always like to do a little sanity check. Well, the 5-inch side and the 8-inch side are the smaller sides in both of these triangles. And so this side needs to be bigger than the 5-inch side, and this side needs to be bigger than the 8-inch side, and they both are. So I'd say, yes, that looks good. I could also just recheck my arithmetic. I could also, in my calculator, do 5 divided by 8, and then do 7 divided by 11.2 and make sure that I get the same result. So lots of different ways that you can convince yourself that you did it correctly. The next thing that we're going to look at is the Pythagorean theorem, and this is another way that we can figure out what sides of triangles measure. And so way back in ancient Greece, there were a group of mathematicians called the Pythagoreans, and they figured out using squares that anytime you have a right triangle, again, this means it's a 90-degree angle here. So a right triangle, that's what this is telling me. Then the side that's opposite the right angle, that's this one here, which normally we label C when we're talking about the Pythagorean theorem. So if I square this, I get the exact same number as if I take both of these two smaller sides, which we call legs, square them and add them up. So in words, we say the sum of the squares of the legs is equal to the square of the hypotenuse, or a squared plus b squared equals c squared. Now, when you're solving these, make sure that this side is always hypotenuse, and these are always the legs. I've seen students, sometimes we might be given, so if I'm given this triangle here, and I'm told that this is 7 and this is 3, then sometimes students want to say, oh, 3 squared plus 7 squared, and then that'll give me whatever this is. What's wrong with that? What's wrong with that is that this is a hypotenuse and not a leg. And this is a leg and not a hypotenuse. So to solve this, I need to put 3 squared plus x squared equals 7 squared. And then I can do a little bit of algebra. So I have 9 plus x squared equals 49. And then I can subtract 9 from both sides. So I get x squared is 40. And then I can take the square root of both sides. So x is the square root of 40. So just make sure when you're solving problems in your homework that the hypotenuse is all by itself and the legs are on the other side of your equal sign. All right, that brings us to the next one. So let me share the next 10.4. There we go. And in this PowerPoint, we're going to be looking at area and circumference. Right, area and circumference. So we'll start with the area of a rectangle and a square. So if I know the measure of the length and the width, a rectangle basically just has 2 dimensions. So a rectangle has 2 parallel lines opposite 2 more parallel lines, and then all of these angles are 90 degrees. And so the formula for the area is just the length times width. What we're really asking when we're trying to find the area is we're really asking ourselves, let's just assume that each of these are 2 units. So this is 2 units. And let's assume this way we've got 4 units. Okay. So how many little square units that are 1 by 1 like this? This is a little 1 by 1 square. How many of those does it take to fill the rectangle? Well, it takes 2 times 4, 8 of them. So we can always just measure length times width. And then when we talk about a square, remember a square has length and width the same. It's just a special case of a rectangle where all 4 sides are exactly the same. So instead of length times width, we have side times side, or side squared. That's why we call this squared. And then we can do a slightly more complex problem, and you'll see some like this in your homework. And for this one, really, I think the easiest way is to just break this up into two rectangles, okay? And you can either cut it here, and then you've got this rectangle and this rectangle, or doesn't matter, you could also cut it here, whichever way makes the most sense to you. So if I cut it this way, notice that this rectangle, what are its dimensions? Well, it's 6 feet in this direction and 3 feet in this direction. So this guy has an area of 6 times 3, which is 18. Now for the other rectangle that's oriented horizontally, I have this dimension, it's 3. But this dimension, it's not 13. 13 only gets me to here, right? And I also need to measure all the way over to here. So this distance is going to be exactly the same as this distance. This is 3 feet, which means that this dimension here is 13 plus 3, or 16 feet. And so this upper rectangle has an area of 3 times 16, which is 48. So the area of the entire L shape here is going to be 48 plus 18, or 66. And then my units are square feet, because I was asking myself, how many little squares that are 1 foot by 1 foot can I put in there? And we had also broken it down this way. Notice that we end up with this rectangle and this rectangle are a little bit different, but they still add up to 66 feet. In other words, it doesn't matter which way you break it up. We could actually break it up a third way by figuring out this square. It's more complex, but it would also work. So we could do the blue rectangle, the green square, and the orange rectangle. That would work too. So you just want to break it up into rectangles whose areas you can find, and then just make sure that you are measuring those rectangles correctly. We can also build on this idea and find the area of a parallelogram. And a parallelogram in geometry has opposite sides that are parallel. So a rectangle is a case of a parallelogram, but a rectangle is a special parallelogram because it has all 90 degrees angles. But the general parallelogram, like the one that you see on the left here, doesn't have all 90-degree angles. The angles have different measures. But we can always take this little piece off, this little orangish piece, cut this little piece off and tack it on over here. And we get this. So you can see that as long as I know the height, the distance from between these two parallel sides, and I know the base, I can find the area, the same as for a rectangle. So base times height. Now be careful, one common mistake I'll see is that if we're given that the base is 10 and this side is 8, okay, we don't care what this side is. We care what the height is. So if the height is 6, then the area is going to be 6 times 10, or 60 square units. It's not going to be 10 times 8, okay? So make sure that we use the height and not the length of that side. In the rectangle, they're the same, but in the parallelogram, they're different. All right, so here's another example. So in this one, we're only given the base and the height. Okay, but you could imagine cutting off this little triangle and tacking it on over here. And now I have an 8 by 4 rectangle that would have the same area as this parallelogram. Oops, I went too far. And that brings us to a triangle. So for a triangle, I could imagine taking this little triangle here and reproducing it, whoops, exactly right here. So this side is equal to this side. And then the triangle over here that I'm going to make green, I could make a copy of it and tack it on over here. And now I have a rectangle that has dimensions base times height. And my triangle is only half of that rectangle because I made copies here. So that gives us the area of a triangle is 1/2 base times height, or half of the rectangle I would get if I use the given base and height. And when we're finding the area of a triangle, we can find it, we can always find it multiple ways. So here we used this base and this height. But if for some reason I didn't know this particular height or base, but maybe I know what the length of this side is, well, then I would need the height. So in other words, see, it looks like if I kind of come right, I'm not drawing a very good straight line, but whatever line goes from this point to here and makes a 90-degree angle, that's my height. Okay, so if I have this base, then I need this height to go with it. And similarly, if I know the measure of this base, then I need the measure of this height that goes from this opposite side and makes a perpendicular. So those will all give me equivalent areas. And which one do we use? Well, whichever one we have. So whichever base and height I have, that's the ones that I'm going to use to find it. And here's an example. So notice that in this example, I'm given all three sides of the triangle. So I have to decide which one I'm going to use to find the area. And the one I'm going to use is the one whose height I know. So from this point here to this opposite side, I have a height of 10 meters. So that means I want to use this to be my base. So the area is going to be 1/2 base 16 times height 10. So I get 80 square meters, or 80 meters squared. And then we have a trapezoid. And kind of related to a parallelogram, but in a trapezoid, we only have one pair of opposite sides being parallel, and the others are not. So in this one, you can see that DC and AB are the parallel sides. And so if we think about this yellow triangle here, this yellow triangle has base A with a height of H. So the area of this yellow triangle is 1/2 A times H. And then if you think about this orangish colored triangle, and if I am using side DC for my base, and I want to go from the opposite vertex and drop a perpendicular, notice that I have to extend this line out here to get this height. So the area of this is going to be 1/2 the base B times the height H. And then if I add up these two areas, I get this 1/2 AH plus 1/2 BH, which I can write by factoring out the 1/2s and the H, and I get 1/2 H times A plus B. Another way that I think of this is it's the average of the bases. That's what 1/2 A plus B would be, the average, right? Add them up and divide by 2. That's the average of the bases times the height. It's another way of thinking about this same formula. So I like to have ways of remembering it so that I'm not just memorizing. All right, so how would I find the area of this one? Again, I have to pay attention because I'm given more information than I need to solve the problem. It doesn't matter what these are. These are extra information for this problem, because what I'm interested in is the height, and the height, remember, is the distance between the parallel sides. So that's 32 is parallel to the side that's 46, and the distance between them is 13 feet. And I know that because this is perpendicular here. So this is my height. And then these are my bases. I'll call this one A and this one B. So plugging into my formula, 1/2 H times A plus B, I have 1/2 times 13 times 32 plus 46. I switched them around, but that part doesn't matter. And then if I simplify, I have 507 square feet. And now we're going to switch gears and talk about a circle. The definition of a circle is that it's a set of points in a plane. So again, think a flat sheet of paper or this flat surface of the screen that we're looking at. And every single point that's part of the circle, it has the same distance from a given point, which is called the center. And so if we draw it, we can start with a center, and then I'm going to go all the way around the center so that every point is the same distance. And then we call that distance the radius, and we use an R for radius. So this distance here is R, this distance here is R, they're all R. Anytime I draw from a point, from that center point to a point on the circle, it's going to be R. We also talk about the segment that goes through that center, starts on one side of the circle, goes through, goes through the center. Let's see if I can do that, and hits the other side. Okay. So notice that this is a radius and this is a radius. And so that distance is going to be 2R, and we give it a special name. We call it diameter. So we use D. So when you're doing some of these problems, sometimes you're given the diameter, sometimes you're given the radius. I always like to draw it out. And if I'm given the radius, I label it. And if I'm given the diameter, I draw it in and label it. That way I have a nice pictures to help me. So just be careful because sometimes you're given one and sometimes the other. And we usually use radius in our formulas, but sometimes we use diameter as well. And again, it was the ancient Greeks who made this discovery that there's a constant ratio between the distance, the diameter distance that goes from one side through the center to the other side, and the distance all the way around. And they found that every time they did those two measurements and they took the ratio, they took the circumference and divided it by the diameter. Every time they did that, they ended up with this number, which we call pi. And we usually use, in this class, we'll use 3.14 as an approximation. So that means if I know the diameter, I can multiply the diameter by 3.14 and I'll know the circumference. And when you're doing problems, sometimes it'll ask you for the exact answer. So in this circle, we have a 40-yard diameter. So the circumference is pi times 40, or 40 pi. This is an exact answer. So in math, sometimes we want the exact answer. This would be it. But you'd be really hard to find someone who could cut you a length of rope to be 40 pi yards. So most of the time we take an approximation. We just multiply by 3.14, or we might take more digits. We can take as many digits of pi as we want, but this is probably accurate enough. So multiplying by 3.14 and rounding to one decimal place, I get 125.7 yards. And I would use that as the approximation. So the difference between the exact answer, it's going to have pi in it. Remember, pi is just a number. So 40 pi just means 40 times the number that's 3.14, and the digits go on forever. The approximate answer, what I call the Home Depot answer, if I'm going to Home Depot and I want to give them a length of something that I want to buy, then I have to approximate. So we might have a problem like this one, which is a better deal? A large pizza with a 16-inch diameter, that's a pretty good sized pizza, costs $15. And a medium pizza with an 8-inch diameter costs $7.50. So if you just first look at it, you might notice that, oh, the diameter in the large pizza is twice as big, and the price is twice as big. So does that mean they're the same? Well, we don't really, if we're thinking about how much pizza we get, we're really more interested in the area than in the diameter, right? So we can calculate the area of both of these pizzas. And the area of the large pizza is going to be pi times r squared. Well, excuse me, we're given the diameters. So for this one, I have to figure out what the radius is. So if the diameter is 16, that means the radius is 8 for this one. And the diameter for this one is 8, so the radius is 4. So for the large pizza, its area is pi times r squared, or pi times 8 squared, so 64 pi. And then using 3.14 for pi, we get 201 inches. For the medium pizza, now we have pi times r squared, so we have pi times 4 squared, or 16 pi. And if we substitute 3.14, we get about 50 inches. So you can see that the large pizza with the diameter that's double the small is actually 4 times more pizza. So definitely the larger one is going to be the better buy. All right, now let's look at a few questions from last week. Oh, I need to share this one. All right, so this type of a problem, and we worked a similar one in the lecture, but let's look at this again, and I'll make up some different numbers just to make it more interesting. Oops, sorry. There we go. Okay. All right, so let's say this is 33 degrees. And then let's say this one is 82 degrees. Okay. So kind of like the one that we had in the lecture, the first thing that we want to do is try to figure out how can I find another angle? Well, here I know this one, but I don't know either of these. I really need to know 2 angles before I can find the third one in a triangle. Here I would need to know 1 to know 3. And so if I could figure out any of these angles, I could figure out all of them, right? If I knew 1, then 3 would be the same, and 2 would be 180 minus whatever 1 is. So that's not looking promising. I would need one of those. And then here I've got a triangle. And in the triangle, I need 2 angles. And if you, at first glance, you might think I only have 1, but remember, this means 90 degrees. So now I know that angle 1 plus 90 plus 33 has to be equal to 180. The angles in the triangle have to add up to 180. So the measure of angle 1 plus 123 is equal to 180. And then subtracting 123 from both sides, I have the measure of angle 1 is going to be 57 degrees. And we said, well, as long as we know 1, we know 3. So that's going to also be 57 degrees. And then remember we said angle 1 plus 2 have to equal 180. Well, we already figured out here that 123 plus 57 equals 180. So that means this one has to be 123 degrees. Or we could, if we forgot, we could also just subtract 57 from 180. And that leaves us only one more, angle 5. And again, we've got a triangle now, so I have 57 plus 82 plus whatever 5 is, has to be 180. And now I can simplify. So let's see, 57 and 82, I get 139. And then subtracting 139 from both sides, I get 41 degrees. And so now I've got all of them. So just kind of look around, figure out what you can figure out. So we're looking for triangles, we're looking for vertical angles, and we're looking for those straight angles that are corresponding angles. And let's find the next one. Oh, okay, here we go. Okay, so another problem with angles and triangles and trying to figure things out here. So in a problem like this one, I've got this angle here. We'll change this one again to make things, let's call this one 125 degrees. Okay. So the first thing that I notice is if this is 125, I see that these two have to add up to 180. So that means the measure angle 1 is going to be 180 minus 125, which is 55 degrees. And then the next thing that I remember is that these two lines here and these measures tell me that this is an isosceles triangle. And in an isosceles triangle, opposite sides, so the sides, sorry, the sides that are congruent, their opposite angles are congruent. So this angle here, the 55-degree angle, is opposite this 4-inch side. So that means that this angle, which is opposite the other 4-inch side, also is 55. And that gives me a lot more, doesn't it? Because I know that these two have to add up to 180. So I've got a 55 and a 125. So that means this one's also 125 degrees. Or I could subtract. I could do 180 minus 55. And then I also know angle 5 because these are vertical angles. And that gives me one more. I need angle 3. And it's part of a triangle for which I know 2 of the angles. So I can write that the measure of angle 3 plus the other 2 angles that are in the triangle with it, the 55-degree angles, that has to be 180. And then I can simplify. So measure of angle 3 plus 110 degrees is 180. So the measure of angle 3 is going to be 180 minus 110, which is 70 degrees. And I've got them all. Here's one of these true false. Does this make sense? Triangle 1 is a right triangle. Triangle 2 is a right triangle. That must mean that they're similar. When you have a problem like this, go back to the definition of similar. And what did the definition of similar triangles tell us? It told us that all 3 angles had to be equal. So let's think about this. If I draw this right triangle, that's 90 degrees, right? Can I draw another right triangle? I sure can. I didn't do a very good job at it, but look at that. These are definitely not similar, are they? This has a little teeny tiny angle here. And these 2 angles are roughly the same measure, but not necessarily the same measure. So this doesn't make any sense. The definition says that in a right triangle, or in similar triangles, we need all 3 angles to be the same. So just because one angle is 90 and it's 90 in the other one. The other two could be 45 and 45, or they could be 1 and 89, or any other of infinite number of combinations. So this one doesn't make sense. So kind of combine the looking at the definition with a drawing. Can I draw? I really only need one counterexample to prove to myself that it doesn't work. This one's like one that we did in the notes. Let's look at this one because we're running out of time. So we've got a taxpayer who has a home office, and they're allowed to deduct a percentage of their home expenses. And what they can do is they can take the ratio of the office area to the area of the home, and then they can set that equal to the ratio of the electric bill for the office to the ratio of the electric bill to the home. And this is kind of related to what we did with similar triangles. So let's just change this a little bit as well so that we don't do the same problem, but so that you kind of get the idea. So for our office, I'm going to make it I have a tiny little office. I'm going to make it like I'm lucky if it's 6. How far do I think it is in the other direction? I'm going to say it's 6 by 10. I don't know. I'm not very good at estimating. So my office is about 6 by 10. And let's say I have a 1,500 square foot home here. Okay. And I'd be happy if my electric bill was 4,900, but we'll stick with that. That's okay. So what I need to do is I need to compare the office to the home. So just the office compared to the whole home. And whatever the areas are, the ratio of the areas needs to be the same as the ratio. So ratio of areas needs to be same as the ratio of the electric bill. So on this side, the ratio of the areas, well, the home area we said was 1,500. And this area is just going to be the length times width. So 6 times 10, which is 60. Now that ratio is going to be equal to the electric bill ratio. Well, the whole home electric bill was $4,900. And what we're trying to find is how much of that electricity did the office use? That's our missing number. And now to solve this, remember, like with our triangles, we can cross multiply. So 60 times 4,900 is equal to 1,500 times x. Oops, that should be 4,900. Let's fix that. 49. 60 times 4,900, I get 294,000. So now I just divide both sides by 1,500. And so divide by 1,500, divide by 1,500, and I get x is 196. All right, so the area of the office was 60, and that in the ratio is 60 to 1,500 for the home. So the electric bill portion for the office is $196. That's my tax deductible electric for my home office. We have time for one more. Let's see what we have left. We can do both of these. Okay, I drew 2 lines in the same plane that are not parallel and do not intersect. So for this one, I would start by playing around with it. So Let's draw two lines that are not parallel. So here's a line and another line. Well, if it was parallel, it would be like this, right? So if it's not parallel, let's just turn it a little bit. So let's just turn it a little bit. Oops, if I turn it a little bit, it's going to intersect, right? So they are pretty much, you're going to have one or the other, right? Because as soon as you move them away from being parallel, at some point, it may be way off into the distance, but at some point, they're going to intersect. So this doesn't make any sense. Lines that are in the same plane are either parallel, so either they'll never meet or they'll meet. Those are the only options. And then the last question is about the rungs of a ladder. So for this one, I like to just, let's think about what a ladder looks like. So a ladder, so these are the sides, the vertical lines, and then the horizontal lines are the rungs. So the rungs are they perpendicular to each side? Yeah. So this rung is perpendicular to this side and it's perpendicular to this side. And this rung is perpendicular and so forth. All the rungs are perpendicular. Does that mean that they're parallel to one another? Is there any way? Well, if we think about our traversals, right? We can think about these lines as being the rungs as being traversals. So the sides of the ladder we know are parallel. And then we can think of this being a traversal. So since we know all of these are now going to be 90 degree, aren't they? They're all going to be 90 degrees. Every single one. So one way is, well, we know we've got a rectangle, so the sides must be parallel. Also, we can think about the parallel lines and the traversals, and we have all of those congruent lines. So yes, they would have to be parallel. So for these types of questions, go back to the definitions, and if it's anything that you can draw it. If you can come up with a case that wouldn't work, that's a good way to prove to yourself that something is false. If you're trying to prove that it's true, that can be helpful too. But convince yourself why it would never be not true. And that's all I have for this week. If you have questions, please reach out to me through Canvas or at jane.keller@joyce.edu. Have a great week.